Okay, so today we're finally going to get into some wood. We'll look at, start with beams. I apologize, I was looking at this PowerPoint the other day. I can't believe I put it all in one PowerPoint. Maybe I'll break it in half or something when I post it because it's like 99 slides. I don't know. Sorry. And so I just kept adding things onto it, I guess, over the years. Gotten a little out of control. But we won't cover all 99 slides today. It'll take probably a couple weeks to get through it all. And see what the NDS has to say about beams. To start with, it is an ASD approach, and the basis of the allowable stress is in the supplement, this little guy here. And it's there are tables that are separated first by the size of the lumber and the type. So like dimensioned lumber has a set of tables, and then post and timbers, which are the little bit bigger ones, they have a separate set of tables. And then what else do we get into? They make some, for some reason they create a special table for southern pine, which is okay, if that's, and they include the size factor in that table, but that's not that useful, especially not for us because we don't have that much southern pine up here. And then they have some tables at the end that do glulam, and you can always tell the glulam tables because they're landscape. All the other tables are the other way around, but the glulam fit the other way. And in the front of all those tables, they've got pages that give all the dimensions and the sizes. Also on this, it'll give the weights if you for a series of densities, 25, 30, 35, 40, 45, 50. So if you pick one of those densities, you don't even have to calculate the weight. It'll give it to you. And at the front of each table, right in front of the table, there are a series of adjustment factors that pertain specifically to the tables, and it's pretty well organized now. I can remember when I first started using this code, it was very difficult to piece it all together because they put an awful lot of the factors they put as footnotes under the table, which made it very difficult to kind of sort through and find what you were supposed to be applying. But now it's very easy to see. It's all right at the front of the table. And the table itself gives all the different stresses, bending, whoops, okay, cut that out. The bending, tension parallel to the grain, all right? So parallel to the grain would be tension long ways, right, that way. Tension the other way would be almost nothing. I mean, it'd be because the wood would split if you put it in tension that way. So there's very little strength in that direction. And it's not I don't know how you would normally use it like that either. Shear, compression perpendicular, this is generally bearing. ING, okay. And compression parallel to the grain, this would be a column, right? This would be that way, long ways. And then the E moduli. This one is used for, let's see, E min. It seems like it comes into calculation of CL, I think, if I'm not mistaken. We'll see. It'll come up. Okay, and then of course the specific gravity is given there. So just to look at a summary of the factors that go on each of these, it's, we have in the table, the nomenclature is a capital F, so FB would be bending. When you put this little apostrophe on it, that indicates that you've included the factors. So that's the distinction here. If you see this without the apostrophe, that's just the straight value out of the table. If you see it with the apostrophe there, like this, then that means that it's including the factors already. So we include the factors, and that allowable then, or the actual has to be less than what's allowed, right? And the actual is just M over S. Okay, and yeah, it doesn't include any stability calculation or anything. That's all over here. That's wrapped up in the factors. So these are all the factors that apply for bending. For shear, there are fewer factors, some of the same ones. In fact, I guess all of these are the same ones. It's just not as many, not including all of them, not the stability factor and that sort of thing. And the actual stress, VQ over IB for a rectangle, is actually 3/2 V over A. And I don't know if we mentioned it already, but the critical distance for shear is actually at d distance away. It's not really the max. V max would be at the reaction, right? That would be the support, basically. Would be the maximum shear. But because this is in compression, I mean the compressive forces, the principal lines are really more like that. So they take an angle of 45 degrees there and consider that area primarily in compression, not in shear so much. You can imagine if it's splitting this way, I mean it's splitting here, and you have a strong force across it, that's going to kind of not let it split. So it would tend to, the critical distance would be d distance away. But in practice, shear usually doesn't control in wood, in beams in general, right? You realize that because of the span. The span is, did we mention this? Like WL squared, right? It's the over 8. It's the square, the moment goes up by the square of the length, whereas the shear is this WL over 2, it goes up by the linearly, right? So as you make a beam longer, moment becomes critical much faster than shear increases. So and usually we try to have long beams, I mean reasonably long, at least as wide as this room, right? Even for wood. So you end up with moment controlling would be the normal situation. If you have a very heavy load or a short span, then sometimes shear is critical, but usually not. So because it's not so critical, what we usually do is we'll calculate V max, which is maybe a little bit easier than trying to then subtract off the d distance shear. Just calculate the end reaction, the V max, and then and then see if it passes. If it passes, okay, you're fine, because that's bigger than what you really need to consider. If it fails, then maybe you want to sharpen your pencil and you say, okay, well, let's see if I take off this little bit, if that makes any difference. And it would only make a difference on, a uniform load where that would cut, right? If it were just point loaded, it's not going to make any difference because you'd have there wouldn't be any change. Okay, and the last one we won't get into right now, but compression And this one also has a stability factor with it, and otherwise pretty much the same factors, and that is just the P/A type stress on that. And all of these then are summarized in a nice little table in Chapter 4 of the NDS, so you can see, quickly which ones you have to consider, check them off. And usually, most of them are not applicable, right? So wet service factor is only applicable if it's wet, right? If you're dry and indoors, then that's not even going to apply. Or the temperature factor only applies where there are elevated temperatures. So if you don't have that, that doesn't apply. Beam stability factor, you usually try to brace it sufficiently so that that one would be 1. Size factor is almost always applicable because you've got different sizes. Flat use is another one that's almost always 1. Flat use only applies when it's flat. And how many beams are used in a flat use? Very, very rarely. So that one's not very common. In sizing, that's the, where it's got those grooves in it. So that's usually outdoor, the only place I've really seen that in telephone poles and bridges for some reason. Outdoor wooden bridges very often, I think the reason is because they use a denser lumber, a higher grade lumber, but they want to have it protected. So to get it to impregnate that denser lumber, they have to incise it. Anyway, but that's kind of rare too. Repetitive use, okay, for joists, yeah, that would be common. So really, when you look at these, the one that you're likely to use, CF, and if it's a joist, CR, and the rest of them, less often. I mean, you have to consider them, and this one sometimes too. This, for larger beams, CL would be possible. For joists, usually not. It's usually braced well enough. You don't need it. Okay, so now we'll look at those, just to show you where these are in the code. They're spread out a little bit. Some of them are here in Chapter 3. There are a few of them in Chapter 4. And then the rest of them are in the supplement. So this one is in Chapter yeah, and I haven't said that. This one's actually in Chapter 2, probably the one that's in Chapter 2, based on loading, the duration factor. And what they're looking at here is basically this graph. This is in the, what do you call it, commentary. And by, time, as time gets shorter, then it gets stronger, right? It's stronger for a shorter duration. So they set it up so that 1 is what is 1? 10 year live load is 1. So this is 1. Here's 1. And that way, if you leave it off, and they try to do this with several of the factors, which is nice. If you accidentally leave it off, you're still safe, right? Because you wouldn't be taking the bonus of whatever this is, 1.15 or 1.25 for this shorter duration. So shorter durations, the wood's able to carry a heavier load. And it's kind of amazing that that duration stretches out over years, or even at least months, right? So this would be 7 days. That's a construction load. This would be roof live load normally. Snow loads, 2 months. I think. I don't know. It depends where you are, but 2 months would be the most you'd expect to have snow on your roof. So that would be 1.15. This is the live load, right? And then the dead load is permanent. And right. And then any combination, you always take the shorter one. So here you've got dead load plus live load, you'd go with the live load. Dead load plus wind load, you'd go with the wind load. Because as soon as the wind stops blowing, then you don't have that combination anymore. That combination only exists as long as the shortest thing in that combination is actually acting. So live load, snow load, you'd go with snow load. Live load, wind load, you'd go with wind load. Dead load, snow load, wind load, you'd go with wind load. Right? Dead load, live load, snow load, wind load, you'd go with the wind load again. Okay, so those would be how you choose which one. And to decide, this is also kind of interesting with wood. Usually it's pretty apparent what the controlling load combination is. One will be considerably higher. But if, say, you had wind in the equation, say you had both this one and this one. Well, if I use this one, I have a factor of 1.6, which would strengthen it, right? So even though the load might be heavier, that one might end up have the advantage, be stronger, as opposed to a longer duration snow load, which would have a lower factor. So you have to consider the factor in determining which is the controlling load case sometimes. And the way you can do that is for each combination, calculate what the moment is for that combination, and then divide it by the CD factor for that combination, and then compare those numbers, the load divided by CD, moment divided by CD, compare that for all the cases, and the one that's largest, that would control then. That would be your controlling load case. So you got to consider that into deciding which is the controlling load case. Of course, if you weren't sure, you could just do them all, right, and see which one controlled. But you don't really need to. You can determine it just based on the moment and the CD factors. Okay, temperature. This is up in your attic, right? Normally, if you're under 100 degrees, you got 1.0. If you get up to 125, then you've got numbers like this, and it depends on your the different stresses have different values. So most of them here would have 0.7, or even, wow, look at that, cuts it all the way down. If you've got a hot attic, you lose a lot of strength, right? You lose 50% of your strength. Woo! At least in bending. It doesn't seem to affect tension quite so badly, or the E modulus, but these stresses are apparently affected by temperature. Then what else we got? Moisture factor. Okay, now these are in, I should have said where these are, right? Where was the last one? Temperature factor, I think that's in the code. That's in section 233. These are in the supplement. So right in front of the table that would have the values for dimension lumber, they'll give this CM, and it only applies where the moisture content exceeds 19%. So usually that's quite a bit of moisture. Usually you would not. A kiln dried is at least, 18%. Sometimes they'll just rate it at 18%, I think, so they're below 19. But normally kiln dry would be even lower than that. And of course your equilibrium moisture content is much lower. It's like 6 or something, or 5. We should get a little thing. You can measure what do you think the humidity in this room is? I don't know, but it's probably not that much, particularly in winter. anyway. So if you're below 19%, then you just use 1.0. Then it would just be 1. But if you're above 19%, then it depends on which of these you're looking at, and you'll have the appropriate factor. Also, if you have, I think it's fairly, this looks like fairly strong wood. I thought it was fairly weak. Whatever. If you, oh yeah, it's fairly weak, I suppose. If you have a stress under that amount, if the straight FB times CF is under that amount, then you don't even need to consider the moisture. So weaker wood, they don't want to further penalize, I guess, is at least in bending. That's in bending, and this is in compression, right? So those are the two stresses where you have to kind of look at that, the stress level. Okay, and then the size factor. Here we go. This table's in the supplement, and this is the one that takes into account the volume of the member, basically. And as the volume increases, I think statistically you have a greater chance of a defect occurring in a critical spot. So, as the volume increases, you have more defects, I guess. So as you have more defects, maybe there's a greater chance that one will be in a critical spot. And so to account for that, they lower as the volume gets larger, they lower the strength. And they set the baseline at a 12 by 12, a 2 by 12, at least for dimension lumber, right? Or I guess a 4 by 14, if you could find that. And then they increase it as you go smaller. So again, they've set it up so that if you forget to put this on, you just lose the benefit, right? It's not quite as dangerous as, a forget is not so likely to be fatal. Anyway, and here you can see it depends on your bending, tension, or compression. You have different values. It also depends on the grade. These are the normal grades, and then stud grade, construction. These are the ones that are listed, of course, in the table here. And these are for, so if I wanted a 2 by 4, this would be, this would be the 4, and this would be the 2. This would be a 2 by 4. All right, so this is gets a little bit, the nomenclature gets a little bit, the thickness, normally we think of thickness as depth, but that's not what they're calling thickness. They're calling thickness the smaller dimension, right? Or the breadth. That's why they specify breadth, so you understand it's usually that way in a beam. So that's the 2 or the 4 inch, and then this is the depth here, are these dimensions. So you can kind of tell. You just have to be a little bit careful with these ones where they have 4 and 4, or I don't know. Yeah. Okay. And then what do we got left? These are also in the supplement. Flat use factor, that's where it's used flat and would be very stable, so they give you a little bit of a benefit for that. So the wider, the bigger it is, you pick up an additional benefit, 20% if it's a 2 by 10. But that, again, this would be a very unusual when you ever use a 2 by 10 flat-wise. It would not be too common. But anyway, if you did, you can increase the strength of it slightly. And then the repetitive factor, this is much more common, of course, because all the joists are always repetitive. So if you've got joists within less than 24 inches on center, 24 or less, then you can apply this factor. Space not more than 24 inches. So if you have them, for some reason your joists are spaced 36 inches on center, which is probably against other code factors, you could not apply this. They'd be spaced too far apart. The idea is if they're spaced 24 or closer, if one of them's a little weaker, the ones on either side will pick up the difference and it'll balance out. So they give you a little 15% bonus for that. Okay. Oh, and there have to be at least three of them in a row to be even. Yeah, because you'd have to be at least three of them, right? Two of them's not really enough for them to pick it up on either side. Okay, and here's the incising factor. This is also back in the code, I believe. Looks like in chapter 4. This is, boy, look at that thing. I brought in a sample. Didn't I pass around a sample of this the other day, or did I? I forget. Oh, I should have brought it with me today. I have one downstairs. Oh, well. Yeah, you can imagine that when you cut the wood like this, the reason they're doing it is so that you can impregnate the chemical to preserve it. And if the wood is dense, it doesn't just soak it up. You can imagine if it's a soft pine, it's going to soak up like a sponge. You don't need to do too much. But if it's a harder wood, then even a denser fir or a pine, then they'll incise it like this so that the chemical impregnates it a little bit better. But in doing that, it obviously cuts the fibers on the outside, so it weakens it a bit. So this cuts it down. Then in bending, they take 20% off, right? You've lost 20% of the strength there. Okay, but at least it doesn't rot. And now, here's the biggie, the stability factor. And this is the one, like I said, you would normally try to brace it well enough that you would not have to use this. That the idea, this is when I load it, if it has lateral torsional buckling, this is what accounts for that lack of stability. So I load the beam and it flips out sideways. And a thin joist could very easily do that. It has a profile. It's only 1.5 inches by maybe 10 inches deep. If you loaded it, it could easily flip out sideways. So you try to prevent that. The more compact the section is, the less tendency it is to flip out. So if you've got a 2x4, like this guy here, and I loaded it, that's probably not going to flip out sideways. It's just going to deflect straight down. So we don't need there's no lateral support needed. These are all, if you meet these cases, CL equals 1 for all, if you meet the criteria here. So the way this, I should have maybe explained that to begin with. This talks about how you determine whether to apply CL or not, right? So if it's flatwise, then you certainly don't need CL. If it's if you meet this criteria here, 441, then you can take CL as 1. Otherwise, then you have to calculate CL. Okay, so here you'd go down this list for your member and try and meet the criteria. So if you've got as the members get more slender, as they get deeper and deeper, that it has more of a tendency to buckle sideways, so you'll have to do more to brace it. So initially, if you've just got 2x6 or 8, the ends shall be held in position. So that's all you've got to do, is each end, and normally you would do that. right? You have blocking. The joists come like this, and you put a piece of blocking in there, so it's supported at the ends. Okay, so that's easy to meet. If I have a 2x10, which is maybe more likely to be a joist, well, then I have to hold the compression edge of the member shall be held in line for its entire length. Wow, okay, but if I'm putting flooring on it, that may not be so difficult. If I'm putting, I used to have a friend who was in construction. He said he'd always glue and screw, which meant, when he'd lay a floor, he'd glue, and you see people do this. They'll lay a bead of liquid nails or whatever that stuff is, glue it, and then he'd screw it to make sure that it was held, that top edge was held. I don't think the code really requires that, but they require nails at least a pretty close spacing, like I have to check on it, maybe like 3 or 6 or something like that inches to provide that bracing. Okay, so if you have that floor nailed down, then yeah, you can get that. So that's not so hard to get. If you go to a 2x12, well, then you need, in addition, and each of these kind of adds it, right? So we have to have the one from above plus, so it's also, this one also has the end blocking, I think, in it somewhere. And yeah, see here, the end points shall be held. So it includes the one from above. So now when I get to a 2x12, the compression edge has to be held, the ends have to be blocked, plus I have to install at cross bracing or something like that every 8 feet on center. So I have to have, and you've seen this, where you have these cross bracing in a floor joist system, or it can just be a solid piece of wood in there. And if you go to a 2x14, which would be kind of an unusual piece of lumber nowadays, then both edges of the member shall be held in line, top and bottom. So you have to have a plywood roof, I guess, or ceiling, and nail that up to the bottom edge of it. This gives kind of an illustration of the same thing. So you can see this is the ends are held, right? This is what we're talking about, the ends there. This is the nail spacing on the compression edge. Here's the diagonal bracing. It's supposed to be at 8 feet on center or something like that. And then here you've got both edges held plus the bracing. So those are your... Now, if you meet that, and maybe some of these lower ones, this would be very difficult to meet. I don't know whether you'd be... I mean, you're really making a diaphragm out of it at that point. Maybe you wouldn't do this, but these other ones are probably not too difficult to meet, actually. So if you can meet them, you'll end up with CL as 1, which is much better, because if you don't take CL as 1, that means CL is going to be less than 1, and being less than 1, it's going to decrease the strength. So whatever, if it comes out to be like 0.5, well, you've shot 50% of the strength of that wood, right? So not too economical. This then is if you cannot meet this, then you have to calculate it. And you calculate it, this is it, lovely little formula. And first you've got to get the slenderness ratio. And to get the slenderness ratio, you've got to get the effective length. So you take the LU is the braced length, or the unbraced length, whichever you want to call it. The braced length. So that means whatever bracing I have, and maybe that's only on the ends, right? If I've got it braced at each end, then LU would be the full length, the full span of the member. If somehow I have some of that cross bracing in the middle, okay, then LU would only be half the span. It's to the bracing, wherever the bracing is, that's my LU. And then to get the effective LE, I multiply it by a factor. So, and it depends. These are for cantilevers, these are for single span beams, and these are all different load conditions, right? So uniform load would be the most common. You'd look first at a ratio of LU divided by D, and if it's less than 7, then you go with this formula here. If it's greater than 7, then you have a little bit more complex formulas. So you got to make that decision, what that the ratio LU to D, compare it to 7, and that'll give you either that way or that way, right? One of those two. And then, or if it's concentrated loads, then you don't have to bother with that. Then there's only one formula. And you can see as the concentrated loads come closer together, right? I got one in the middle. If I just had one at the center, LE would be reduced by, the LE would be 1.11 LU. So it's a little bit, the effective length is a little bit longer than the LU. As I have more point loads, that gets longer and longer until it gets all the way up to 1.8 of LU. So it could be a longer, the effective length is longer, right? Now, once I get that LE, that goes in to that's the length I use in considering the slenderness ratio, right? So that formula is simply LE times D over B squared on the square root of all that. And that has to be, that slenderness cannot exceed 50. Can't be any more than 50. So if you've got one that's longer than 50, bigger than 50, it's too slender. It's considered too floppy. That would be in danger of failing, instability. So that, first off, has to be under 50. And then when you get that, then that is used in the Euler equation down here somewhere. Okay, so this is basically, I think, the Euler equation. Pretty much. Over the slenderness, right? We normally say L over R, right, would be the slenderness ratio. But this is the slenderness ratio we're using for the wood. And this is, okay, comes out like that. And this is, oh yeah, this is for the E min, right? That's where E min gets used from the, and that's just statistically, what do you call it? Where you have, because wood being organic, as you test pieces, each piece is going to be slightly different, right? It's not like steel that you get this beautiful line that's the same for every piece you test. No, you're testing to get the E modulus, say. You're graphing the stress over the strain, right? And one will go like this, and the next one is slightly under it, and then the next one in between, and so they're not that consistent. So it takes a greater percent passing. I guess this E min is lowers the number a little bit, so there's statistically it's at the whatever end of the spectrum there. It's more passing, I guess. It's 5% pass. I don't know, something like that. And so that's the E that you have to use in the buckling there. Okay, so then you get that, and that goes up in this ratio. You make that, which gets repeated 3 times, and run that equation, and that'll come out with CL. So that's a stability. There's a similar equation in the steel manual, isn't there? It's kind of, I forget what the name of that is. It has that somebody figured out. Anyway, so that's the CL. All right, so those are all the factors that go on bending. With shear, you see they're the same factors. There are fewer of them. The stability doesn't come into it. You still have the load duration, moisture, temperature, and incising. It's the only thing that's critical. This is where you're, and you see you'd leave off that, right? So this would be the max, right? Obviously this normally is going over there, but they're just showing you can leave off that load, right? Like that. So any of the load that's in this area, that's how you determine the shear at D, is leave off that load. Okay. But like I said, you only do that maybe after it fails in shear. Okay, so shall we do an example, huh? Analysis. Let's start with analysis. And for analysis, we're given the member size, right? That's what analysis is about. And in this analysis, there are a couple different ways you can do analysis. You can do a capacity, to see how strong it is. We'll just do this one, pass or fail, right? So safe or unsafe. So initially, we're given the member and we're given the loading, so we can determine the stress on the member. Determine the load and then determine the stresses. Then we check the allowables, right, with the factors in the supplement. And then we simply check to make sure that the factored, we have to put the factor, you have to put the usage factors on there, and then check that the factored allowable exceeds the actual stress. Okay, and then you can check deflection if you want, or bearing would be the other things you might check. Okay, so here we go. This is the one we did, I think, in class the other day. I was looking at it, I thought, I should have, why did I not leave these additional questions in there for the homework? I should have maybe done that. Maybe next year I'll add them on. I made the first homework too short. Sorry. Must have been a disappointment. It was so easy to do, huh? Okay, well, so let's do this one and go ahead and see if the beam passes and fails. So I think the one I did in class, I had a 2x10, right? And it was 16 inches on center, and I determined, in that problem, I determined the weight of it. So I looked up the self-weight, and then I had the applied dead load somewhere. Here's the applied dead load. Oop, no, that's the floor dead load. So that gave me the self-weight plus the applied dead load, gave me the total dead load, and then the floor load, where was the floor load? Oh, it was based on the occupancy. I think this was 60 PSF, wasn't it? Came out at that. Oh yeah, there it is, 60. So I got those, and that gave me, so this is what we had in class the other day as the loading. 88.33 PLF. So that's on one of these guys. Okay, so then the next step would be to calculate the forces that produces. So, if you want to make lovely diagrams, you can do that, or just do it with the equations. WL/2 would give us a shear. That would be the max, right? That would be this one. But like I say, I'll use the max initially, and then if it doesn't pass, I can worry about it then. And the moment, WL²/8. Okay, so that would be my moment. So those are the two I need, and then those are the forces, and we gotta calculate the stresses. the stresses, M over S will give me almost 750, and the shear stress, 3/2 V over A, would give me 52. Okay, so those are the stresses. Now those are the actual stresses. Now I've got to calculate what the allowable stresses is and make sure that these actual stresses are less than what's allowed, right? So we go here. We had spruce pine fir, grade number 2, I believe. And for bending, we've got the 875. And for shear, whoa, very high value, 135. Okay, so those are my the two. Now I've got to put the appropriate factors on them, right? So for bending, I guess these are the two. These would be the factors that I'd want to include for bending. All right, well, wet service factor. No, it's not wet, so that one's out. Temperature, it's not a raised temperature. Stability, yeah, maybe. I'll have to check that at any rate. Size factor, yeah, I definitely have to get the size factor. Flat use, it's not flat. Incising, it's not incised. And repetitive, it is repetitive. So I know I'm going to use that one. They are, what was it, 16 inches on center. Okay, so I've got to find these values. So let's see. Oh, and the load duration, that was based on live load. Occupancy live load is that one, right? That's a live load. Okay, so that's that one. A 2x10. Okay, this is the 2x10, should be this guy right there, 1.1, right? This is for FB, and the shear doesn't get a CF factor. Okay, so that's the size factor that we need. And then repetitive use is pretty straightforward. If it is repetitive, which it is, we've got more than 3, and it's less than 24, so we got 16, so we got 1.15. So those are the only, right? So I think I got, oh no, we still have to get CL. CL, okay, so we've got a 2x10, so a 2x10 would be this guy. I just have to make sure it's got sufficient nailing in it. So assuming that I can meet that I do put adequate nailing on, and it's got a plywood or OSB decking on it, panel on it, then I can meet that. So I'll take 1.0 for CL in this case. Okay, so we put all those factors on there. There's a CD, CL we got. There's a CF, right? I don't know what this one was, or something else, and this was CR. Okay, so that raises it a little bit. I go from 875 to 1100 psi. And then the only one that applied in shear was CD, and that was 1, so that didn't change anything on that one. Okay, so now we just simply check it. This was the allowable was 74, so we just compare that with that, and it looks like that's okay. This is less, so that's all right. And we compare that one with that one, and that one's less. Okay, so they both pass. Okay, and I think I did actually look at deflection on this one just for fun. Maybe to point out some of the deflection criteria in the NDS. In Chapter 3 here, there is a little calculation that you can use to consider creep, long-term deflection. And, in steel, there's not much creep, right? I don't think steel creeps. Concrete, I guess, does a little bit. Wood certainly does. Over time, wood would sag a little more. And so they have a creep factor that gets applied to long-term loading. So the first thing you have to determine is how much of your load is long-term and how much of it is short-term. So on something like a live load, well, most of it's probably short-term. A live load in here, the biggest part of the load is probably you people coming in and out, and you're gone at the end of class, so that's not a very permanent load. The other part of the live load, I guess, would be the tables, or maybe, I don't know, the carpet. It's not quite that much load. So depending on your application, you make some sort of a judgment. And maybe you say, like, 30% is long-term, and what's left then, 70% is short-term. Maybe and that's a little bit of it, yeah, obviously a judgment, but I think that's a number that I've seen used quite a bit, 30-70. Or, you could do it 50-50, depends on what your application is maybe. And then you would apply that, let's see, so the percentage that's long-term, it gets this creep factor. And the creep factor depends, this is in that section 3.5. It gives a whole paragraph, actually. I just summarized it, shortened it, but they describe pretty exactly what the 4 classes are. But most of them would be this, dry seasoned lumber, right? If it's in wet conditions, then you raise it. If it's wood panels, okay, apparently creep more. And CLT has more of a tendency to creep, I guess because it's cross-laminated. Maybe the creep is in those other lambs that are, I don't know, somehow it's more likely to. So if we had a creep factor of 1.5, we could say 1.5 times 0.3 times what we calculate as the deflection, 0.21, right? Plus no creep factor, 0.7 is the other part of it, right? Times 0.21, right? And I could add that up, and that way I'd be taking into account my, I'd be increasing by 50% that third that is long-term, right? So that increased it a little bit. I don't know. I don't have a calculator. Somebody want to calculate that? Yeah, there we go. My calculator guy. Let's see what it is. How much difference it makes. If we're still safe. You can give it to me in 2 parts, maybe. This would be...
Oh, it's around 1.09. Is that right?
1.09, no.
Oh,
Have to, this,
1.24.
okay. 0.24. That sounds more likely. I don't know. This should be 2 numbers here, but it should be just a little bit more than that 0.21, right? 0.24, and in this case, if the limit was L over 360.
Oh, yes.
Is that, you agree now?
Yes.
Okay, good. If the limit is L over 360, wherever that is, roof members, no. Not supporting, well, whatever. Then this would be the limit, right? L over 360. So we'd still, even at 0.24 would be under that, so we'd be okay. Most of those, and to be honest, most of the deflection limits are based on bounce, right? So it wouldn't even apply to this. This wouldn't affect that. This would only apply. Creep would be something that would be, if it deflected so much that it caused damage to the ceiling or something under it, or was sagging so much that it somehow was a problem. Not the bounciness of it, which is normally what those deflection limits are about. Okay, and bearing. Oh, we even looked at bearing. Look at this. Okay, so, and here in, this is also in chapter 3, we have a little bit of, you can consider bearing. And the first thing to notice is, where does it say it? Any length at the ends of a member. So what they're saying here is this value as it is applies to bearings at the end of a member. In other words, it's a little bit hard, the way they word it, it's kind of weird, but if it's at the end of the member, you don't apply this CB factor. This CB factor would not apply to ones at the end of the member. It only applies if you're less than 6 inches, and for bearings not nearer than 3 inches to the end of the member. So you'd have to have a situation, where your beam was like this, right? Okay, and there the bending, this would be critical. And what's happening is it's crushing on either side is the reason that's not at the end of the member. And that crushing then allows this to sag somewhat. And it's really a limit on how much tolerance you want to take in it crushing. It's a crushing limit. And I think that turns out to be 3/8 of an inch, maybe. I should have drawn a little picture of it maybe to figure that out. But so depending on your width of your bearing, you can have a different factor. So if the width is only a 1/2 inch, then you've got pretty high factor. If you're over 6 inches, you don't even apply it. If you're up around 2 inches, then you've got a factor of 1.19 or something. So this CB factor goes on to the bearing stress, right? So that FC perpendicular, and you'd multiply it by FC, multiply that to FC perpendicular, and that would be the bearing factor. But in our case, it's at the end, so since we're using it at the end, there is no bearing factor. I mean, it doesn't apply. And we just look at the bearing stress, and make sure that is less than the allowable. This was, I guess, out of the table, right? That value. Okay, so that passes. All right, good. So, I don't know, let's see, we got time. We got 20 minutes, huh? We could maybe get through another example, if I don't go so slow. This would be another, it says it's a a design procedure, but really this is also another analysis, isn't it? Because I'm taking the size, and given the size, I want to try to design the on-center spacing. So this is pretty common for like rafter design, joist design. You can easily pick the size of the member, and then you tune the strength by what their on-center spacing is. If the load's pretty low, maybe you make them 24 inches on center. If the load's pretty high, maybe they got to come down to 12 inches on center. So you've got a choice of, and of course that spacing has to match up with the panels that are being put on it, the 4-foot wide panels. So that's why you have to come down to multiples of 48, I guess, right? You gotta have 16 inches or 12 inches or 24 inches. Those would be your choices. And there's another one I think they use up in Canada. What is that? Or someplace. It comes out to be an uneven number, and it's like if I divide 48 by 3, maybe that's what it is. It comes out to be 18.5 or something. I forget. Anyway, there is another spacing. Okay, so again, we're going to determine the load, find the moments, calculate the stresses, and then look in the NDS at the allowable stresses, and then apply all the factors that we need, and then choose the spacing. So to determine the spacing, ultimately we look at a utilization ratio and then use that to choose which spacing we want. Okay, so I think this was a problem. This is the one, there was one problem. I decided there were too many homework problems at the beginning, and I cut one out. That's why the number, if you look at the numbering, it goes 1, 3. And I'm sorry, I mean, I could correct that, but it's a pain to correct, so I haven't bothered to do it yet. I figured you'd understand what, there is no number 2, or it's just the numbering there. So this was number 2, the missing number 2. And the big part of it was actually calculating the snow load, I think, is why I decided it wasn't really so necessary. So you were given a city, Gaylord. Where is Gaylord? Oh, I can see it. There's Gaylord. Okay, so that looks like 50. PSF is the, and then the terrain is C, exposure, partially exposed, thermal, not slippery roof. So all this is to calculate the snow load in Gaylord. Risk factor, roof span, we say is 30, and it's got a height of 5. Okay, so looking at these different ones, potentially we'd want to find the moment here, right, and divide it by 1.25, and the moment here and divide it by 1.15 and see which of those. Yeah, I guess you could do that one too, but that's not going to control. And then you see which of these controls, but I think this is the one that's probably going to control. Okay, so let's see. Live load. We're looking at rafters, so the rafters are only going to have a tributary area on either side of the rafter, right? So if they were, we don't know what the spacing is, but say they were a foot on space, this is only like 20 maybe, it's 15, this is maybe 16 feet times a foot, 16, so it's way less than this, so it's definitely, it doesn't have much area. And here we've got, I think we've got 4, right? This is 5 foot, this is 15 feet, so that's a third. So that's, should be 4 in 12. Okay, so we've got this guy right here. So we've got that. Okay, so that means this is 1 and 1 for R1 and R2, so we should have 20 for that. Okay, and now, oh boy, the snow load. Okay, from the map, the ground snow, oh, that should have said ground snow, really. Misprint, sorry. That should be ground snow, is 50, and then to get the flat roof, we knock off 30% and multiply these factors, right? So, let's see what they are. I think that'll go. This is the, oh, does that look like Gaylord? I don't know. Probably. It's flat enough. Exposure C. So, I mean, yeah, this is number C here. And we said it was partially exposed, I believe. So, I think that's the one we want, is that one right there. So that'll be the exposure factor. The thermal factor, I think I said to use 1.0, which is interesting. It's not even a cold roof, huh? Usually, like I said, a cold roof would be 1.1, but okay, we'll go with 1.0. Won't give it any additional. And the importance factor, that would be for snow, that would be this, and we're going to take category 2. Alright, so there's our importance factor. So it looks like we got 1 for that, we've got 1 for that, I think we've had 1 for everything, huh? And then the CS, so this was 1, 1, 1. Okay, so that came out to be 35, is just 0.7 times the 50. And then this is for a CT less than 1. We had a 1.0, okay, less than or maybe equal to 1. And we have a slippery, or no, a not slippery roof. Okay, it would be this roof here. Okay, and the slope is 4 on 12. So we got that. So there's where we are. That right there on that graph. So CS is 1.0. So we got CS is 1.0. All right. So that keeps it at 35 then. Okay, CS didn't affect it. So if we've got, then this is 35. This would be, what did we say? This was 1, whoops, 1 times 50 was the ground snow. Okay, so for the balance, the full load across would only be 35, but if I'm dealing with rafters, I've got to design it for the load that would just be on half the roof, right? Because you don't know which way the wind's going to blow. You're going to make both rafters the same. So I'd have to take this one here. This would be the more severe case. That would be 50 PSF for the unbalanced case. Okay, so then that gives me my 50 PSF, and that's the snow is projected, right? It comes down from above as a blanket, and this is I guess this must be the dead load that's on it, right? The surface on the dead load on the surface. So I have to I've got to convert this into this. I could take my 50 PSF and spread it out, but that gets to be kind of a nuisance. Then I've got to, I've got a load coming in like this, and I'm trying to span it like this. I'd have to find the component of the load that was actually causing the bending, right? Because in reality, with the load coming in like this, Some of it is going into compression. I mean, this would be the reality of this, any slope rafter. Some of it goes into compression, and some of it, the normal component, is causing flexure, only the normal component. So the easier way to calculate that is just to put it all into the projected length. So this is using the projected length. I convert not the 50, I leave the 50, but I convert the 7. So I take 7 times 15 divided by, or 15.8 divided by 15. So it increases. I've taken that load that is over the full length and I'm smushing it down. I'm compressing it onto a 15-foot length. So it's got to go up a little bit, right? So it goes up by 0.38. Okay, so we got that. There's the dead load. There's the snow load. And now we can just calculate the shear in the moment. So there's shear, end reaction, and the moment 1614, I guess. Okay. So this is then the actual, then I convert that to stress. Here's, right, the moment section modulus for the, what was it, a 2x10, I think? I forget. It looks like it. And that gives me an FB of 905. Then we compare that to Hem-Fur. Is that what we're using? Grade number 2. Okay. That would be 850. Okay. Put the factors on it. This is snow, so we've got the 1.15 for sure. CL, I think we're probably going to take 1 for that. CF, we got to find. CR, it would have a CR. Okay, so 2x10, yeah, that is what we're using. Again, there's the 1.1 snow load, 1.15. Got that guy. Repetitive use, it is going to be repetitive. The rafters, so 1.15 again for that. This one, again, I'm going to assume that it's nailed, so we'll meet that. Okay. And that gives me all these factors, which comes out to that. Right? So my 850 goes up to 1236, and now I've got the actual at 905. If I make a ratio of that 905 to the 12, that is how much I could, that would be the utilization. So I'm only utilizing 73% of the strength of it. So I could, this was based, well, or this is based on a 12-inch on center is how I got, I mean, I was just using the straight PSF, right? Assuming a 1 foot on center. I used, I used the straight PSF, so it was assuming a 1 foot on center. So now I could spread that out a little bit, right? I don't have to use a foot on center. I could go up to this ratio, 12 divided by this utilization ratio, and that gives me 1638. So we round down to 16 inches on center. So that should work then, 16 inches on center. In fact, if you want to check it, 905 is the actual at 12 inches on center, times 16/12 brings me up to 1207, and 1207 is less than the 1236. So, bang, we got it. That would be 16 inches on center for a 2x10 in Gaylord, Michigan. Okay, all right, I think we can stop here. This will be where we'll pick up a capacity analysis. Oh, that sounds fun. All right, good. Right. We do meet Tuesday, right? I was going to say we didn't meet Monday. No, we don't meet Monday. We will not meet Monday, but we will meet next week, Tuesday, right? What were you going to ask me?
I was going to say, would you ever go less than 12 inches on Saturday? Or is that just less practical?
Yeah, that would. There's no code reason that you could not. You could, but it's a matter of economy, I guess. If you're going that close on center, you probably could do better just to get a deeper beam, and not because you've got to think the other expenses in going that close on center. First off, you've got to buy that many members, and that's probably more expensive than just getting a slightly deeper member and spreading it out. So that would be part of it. Then installing it, you've got to nail all those things. Oh my gosh! And then just the logistics underneath at 6 inches on center. It's awfully dense. I mean, to get mechanical stuff, and so yeah, normally you would never go less than 12. I mean, those are the options is 24, 16, and 12, or like I say, I have to think about this 18 and a half or whatever the other one is. There is another one, but it's an odd one, and it would only be, I mean, you could use it, I guess.
And so, like in that example, if we had gotten it to like maybe like our answer was like 20.3, we just call it like 24 inch spacing, or like 18.
Yeah. You have to round down.
Yeah. Sorry,
Right. Yeah, you have to round down. And my feeling is, I mean, some they'll say, oh, if you're within 2%, that's okay. But I mean, if it were me, the more you do this, you kind of become more and more conservative. That why risk it? Why risk it being becoming a problem? If it's close, I'd just say go to the next larger piece and not worry about it, rather than risking, cutting it too thin and then have people complain about the floor being bouncy or cracking or whatever might result. It's not worth the risk, I don't think. All right. Okay. Very good. Have a nice rest of the weekend. We'll see you next Tuesday.